Hello, welcome to everybody. So we'll introduce the first session, which is devoted to planets of our solar system, actually terrestrial planets of our solar system and how they work. So just a few words to explain why we started with such a session, because Xavier Le Pichon was strongly devoted to geodynamics on Earth. He never really worked on the other planets, but we thought that in the spirit of having a scientific meeting, it would be good to place the Earth in the context, and so to address the planets which are the most similar to the Earth, which are the terrestrial planets, so we will not talk about icy satellites and so on, in order to highlight the similarities and differences. In fact, although the terrestrial planets are relatively similar to the Earth, there is a great diversity with respect to the Earth and of the planets with respect to each other. Of course, the first big difference is in the masses, because Earth and Venus have about the same mass. Mercury and Mars, it's about a tenth. And if we add the Moon as a terrestrial planet, of course it's a satellite, then we go down to 1% of the mass of the Earth. But more strikingly, it's the composition. So Earth and Venus have a core that accounts for about 30% of the total mass. Mars is similar, a little bit less, because it's a more oxidized planet, so there is less metallic iron that can go into the core, so the core is about 25%. But then when we go to Mercury and the Moon, it's totally different. Mercury has a gigantic core comprising more than 70% of the mass of the planet. And the Moon is the complement, because the core is very tiny and it's a mantle object. Another striking property of the Earth is the magnetic field. Today, only two of the terrestrial planets have a magnetic field. It's Earth and Mercury. There was a magnetic field on Mars, and we know that because we have paleomagnetic signatures in the rocks of Mars, the most ancient rocks. So as you can see in the bottom left plot, the paleomagnetic signatures are on the highlands of Mars and in the younger terrains, which are the major basins like Hellas or the North Pole Depression. There is no paleomagnetic signature. The same is for the Moon. We have paleomagnetic signature, and the Moon is intriguing because it seems that the magnetic fields comes and goes. There is paleomagnetic signature for the very ancient rocks around 4 billion years, for 3.8 billion years. Then the magnetic fields goes away, and it seems to come back 1.5 billion years ago. Now there is no magnetic field again. Earth is, of course, characterized by plate tectonics. That's great work by Xavier Le Pichon, and this is unique. Right? Only the Earth has a plate tectonics, but this doesn't mean that the other planets are dead. So there is evidence for convective mantle dynamics going on in Mars and Venus, at least. So Mars, for instance, has the Tarsis region, which in some sense is the analog of the ocean islands. So a sort of plume that is extruding to the surface and building an uplift in the crust. And on Venus, there are these regions called tesserae, which are these ones blinking with the white borders. And so there are various models on how they form. So these are also uplifts of the crust. And the most popular model is related to mantle convection, even if this is not plate tectonics. So it's sort of rudimentary plate tectonics with vertical motion in the mantle that perturb and the thickness of the crust. In terms of tools to investigate the internal structure of and the geodynamics of terrestrial planets, we find basically the same tools that are used for Earth. So a key player is, of course, seismology. In Earth, we have this fantastic seismic tomography showing the dynamics of the mantle. Seismology on other bodies in the solar system started in the 70s with the Apollo mission, because the astronauts were placing some instruments, some seismographs at the surface of the Moon, creating the first lunar seismic network, and this gave a number of information on the interior structure of the Moon. Then, of course, we went to another scale with Mars, with the dedicated InSight mission, which major goal was to deposit a seismograph produced here at IPGP at the surface of Mars. This is not a network, it's a single seismograph, but seismometer, but it allows to get insight on the internal structure of Mars, as we will see. And now, of course, with the new interest of go back to the moon with robotic missions and human missions, now it's the time to place many seismometers on the moon and try to reconstruct the network, and hopefully comprising the hidden side of the moon, because there seems to be an asymmetry in the origin of moonquakes between the near side and the far side of the moon. And so the first seismograph, I think, will be placed by the Chinese robotic mission Chang'e something 7 or 8. Another tool which is used to determine the interior structures of planets is to map the gravity field, as it's done for Earth, for instance, by the GOES mission by ESA. And this has been done with a great detail for the moon, thanks to the GRAIL mission by NASA. And then studying also, you can get important information on the Earth, on the planet interior, studying the spin dynamics, so the wobble of the spin axis, the nutation, the precessions, the librations, and so on. This is also used for, for the Earth, because we observe the Earth from the Earth. We use the VLBI array to really to place the rotation of the Earth in an inertial absolute reference frame. For the other planets, it's used. It's done using radio science. It was the case for Mars with the InSight mission. The radio science also allowed to get many information on the state of the core of Mars. And for the moon, it's mostly done by lunar laser ranging, because the astronauts deposited mirrors on the surface of the moon. So by shooting laser beams, we can measure the recession of the moon from the Earth, but also its libration around the rotational equilibrium point. And for Mercury, it has been done using the Goldstone radar. So we will hear about all of this in more detail. So we have 4 invited speakers for the morning. Philippe Lognonnet from IPG in Paris will start talking about the internal structure of Mars and the results from the InSight mission. He was the PI of the seismometer. He will be followed by Rafael Garcia of ISAA in Toulouse, and he will speak about lunar seismology, the results and the prospects, as I say, new gain of interest in the moon. Then after the coffee break, we will have Julia Maya, now at ESA in Madrid, but before at DLR in Berlin. And she will talk about the seismology of Venus, on which she worked a lot, and predictions for seismic quakes that can be detected, and this prospect of making seismology on Venus, that, as you will see, is not as science fiction as it may appear. Last but not least, Attilio Rivolini from the Royal Observatory of Brussels. He will speak about the internal structure of Mercury. Attilio is strongly involved in the Bepi-Colombo ESA mission. And so he will tell us what we know already and what we hope to learn from Bepi-Colombo. So thank you very much, and I will call the first speakers, Philippe, to tell us everything about Mars.